Thank you. Thanks for the introduction. Thanks very much for having me here. It's very nice to be here. I haven't been to CITA before, and I like it a lot. So first thing, I'm just going to tell you a little bit about the Flatiron Institute. I think you've already had some people from there, so you may have heard, but in case some of you haven't. So the Flatiron Institute, it's part of the Simons Foundation, so just a nonprofit sort of freestanding research center with lots of connections, though, to NYU, Columbia, Princeton, various other neighboring institutions. It's named after the Flatiron Building, not because we're in it. That would be probably not logistically very convenient for seminar rooms, things like that. This is our building, though. It's in the Flatiron District, about a couple blocks away. This is what the interior looks like in an artist's rendition or architect's rendition. This is what it looks like in practice. One of my sons using one of the blackboards there. They like to visit a lot. The reason I say this is we're a new institute, founded only in September 2016 when I started. We've been hiring a lot and growing very rapidly. And so one thing is that those of you who will be applying for jobs and work broadly speaking on computational astrophysics, both simulations but also big data analysis, please talk to me if you might be interested about applying for a position there. The other thing is that we host a ton of workshops, and we have long-term and short-term visitors, sabbatical visitors. We really encourage interactivity and a large flux of visitors. And so again, if you're interested in coming and paying us a visit, it's really not that inconvenient to get there from here in particular. I encourage you also to talk to me about that. So first, just a bit of introduction about the main science questions that I'll talk about today. So over the past decade or a little bit longer than that, one of the main scaling relations that's been established in the field of observational galaxy formation is the so-called star formation main sequence, the relationship between the star formation rate and stellar mass of galaxies. This is shown from one of the seminal papers, Nosky et al., 2007, where this is showing star formation rate versus stellar mass at different redshifts, so around 0 going up to around redshift 1. And more recent work has extended this to much higher redshifts, where you see that there's a population of star-forming galaxies that form a relatively tight, roughly linear relation. And then there's these galaxies that have essentially negligible star formation rates, the red and dead so-called quenched galaxies. Given their masses, there tends to be more of those at higher masses, and there tend to be increasingly less quiescent galaxies. That mass scale at which you have galaxies become predominantly quiescent, that moves up as you go to higher redshift. And then there's also a population of transition galaxies in the so-called Green Valley. So one of the fundamental questions in galaxy formation, I would say even still to this day, is whether this is something that has some deep physical meaning, gives us insight into the process of star formation. Some people have argued that it's actually just sort of a inescapable conclusion of statistics, and you could just have stochastic growth that would give this sort of correlation. So one thing we want to know is what sort of physics can we actually extract from this observed correlation, both from the slope of the relationship and also the scatter, because the relation is quite tight. The intrinsic scatter is something like 0.3 DAX or so. Related to this, there's a population of galaxies that are not on this so-called main sequence, the galaxies that are elevated above it. So, meaning the star formation rates at fixed stellar mass are much higher, maybe even a factor of 10. Excuse me. Than one would expect if they're on the main sequence. Normally, I don't have so much trouble with mechanical things, but I am a theorist. So. All right. So this is a plot from Rodriguero et al., 2011, where this is showing for infrared derived star formation rate versus stellar mass at around redshift 2. You have this relation, the so-called main sequence galaxies, and then you have a population of galaxies that lie well above this, this main sequence. And the question is what is the physical nature of these galaxies that have much higher star formation rates than one would expect for these steadily star-forming main sequence galaxies? And the observed fraction is something like maybe, this depends on redshift and on mass, but in the Rodriguero paper, they quote something like maybe a few tens of %, so not necessarily a dominant population. But the question is how important are they, and what drives them physically? Do they have something to do with this quenching process? On the right, I show a plot from, this is a paper that shows it's a semi-empirical model that we developed. This is showing the contribution of different modes of star formation to the infrared luminosity density as a function of redshift. And on the right, this is showing the star formation rate density, assuming that the AGN are not contributing to the infrared in this model. What you see is that in our model, at least, at all redshifts, this normal disk quiescent mode of star formation, so galaxies on this main sequence, tend to dominate the star formation. And starbursts induced from galaxy mergers constitute something like of order 10% of the overall star formation. So at least in this model, they're not a significant contributor to the overall to the stellar mass formed over the history of the universe. However, this is something that was an empirical model that, as part of it, it had folded in scaling relations developed from binary hydrodynamic simulations of major mergers with quite old models for star formation and stellar feedback. And a lot of the conclusions that we derive from those works over the past of order 2 decades, those are being revised with new simulations, which I'll talk about a bit in this talk, that have much more advanced models for star formation and stellar feedback, and also much higher resolution. So it's unclear whether this conclusion still holds. Now, one of the other important topics I'm going to talk about is nicely summarized by this quote from Andrei Kravtsov, that understanding galaxy formation is equivalent to understanding outflows. The reason for this can be understood if we look at the stellar mass to halo mass relation. The way that this is plotted here is it's the stellar mass divided by the universal baryon fraction times the halo mass. So at unity, if this ratio were unity, that would indicate 100% efficiency. What we expect, just in the presence of gravity and cooling, that gas that's accreted onto halos over a Hubble time would all collapse and be converted into stars. However, when we look at what we infer from observations, and this plot is often surprising to people because it's a bit backwards in the sense that the simulations are the data points and the observations are the lines here. So for those of you who are familiar with it, these are coming from the so-called abundance matching technique. I'm not going to go into any details about that. But the key takeaway I want you to get from this is that at all halo masses, star formation is, globally speaking, an inefficient process. So the peak efficiency of star formation at seemingly all redshifts seems to be at halos of around 10 to the 12 solar masses, and it goes down at both higher and especially at lower halo masses. And what you see is that these simulations, which I'll talk about in much more detail later, but these are a subset of the original simulations from the FIRE project, the FIRE 1 simulations, they have good agreement with the observationally inferred stellar mass to halo mass relation. And the reason that you have this very low efficiency at low halo masses is efficient stellar feedback that drives outflows. And so in general, let's say I accrete 10 solar masses of gas from the IGM onto a halo because of this process of star formation and the subsequent stellar feedback from processes like supernovae. In the very low mass galaxies, maybe 90% or even more of that gas actually isn't converted into stars. Instead, it's blown out of the halo and never is formed into stars. And that's, in these simulations at least, what is causing this low global star formation efficiency at these low halo masses. However, this process of outflows is still not very well understood. The issue here is that in order to capture this entire process, you need to capture cosmological scales. You care about gas accretion onto halos from the IGM, but then you also care about star formation. So you're talking about the scales of at least giant molecular clouds and even smaller, and the stellar feedback processes like supernovae explosions and radiation pressure on dust grains from massive stars that operate on those scales. So this is something that's extremely challenging to do just with brute force simulations employing first principles. And so often what people do in large volume cosmological simulations like in Illustrious or Eagle, which many people may have heard about, or in semielliptic models, is they take some scaling relation for the mass loading factor, which is the ratio of the wind mass outflow rate to the star formation rate. So that number I talked about, given 10 solar masses that are accreted, what number of those is kicked out versus going into stars. And how that scales with galaxy properties, like the galaxy circular velocity as a proxy for the halo mass and thus the depth of the gravitational potential well. So there's some scalings that are motivated by basic physical arguments that typically these simulations, large volume simulations and semi-analytic models, they assume these scalings with some free parameters. Then they go ahead and they calibrate their model to match things like one of the prime constraints is the redshift 0 stellar mass function. They tune their model by adjusting these parameters in order to match these observational constraints. But as you can imagine, these parameters are degenerate with other free parameters in the simulations or in the semi-analytic model. And in some simulations, like in the fire simulations I'll talk about, we can arguably predict the mass loading factors, or at least come much closer to predicting the mass loading factors than one can do in these type of large volume cosmological simulations and semi-analytic models. But then this is still a matter of debate, and people are still actively working on this. And so what this slide shows here is you don't have to worry about what the individual lines mean, but this is just this scaling of the mass loading factor versus circular velocity that's assumed in different large volume simulations and semi-analytic models. And so you see that different theoretical groups disagree both about the slope and the normalization quite drastically. And so and things like Eagle and Illustrious and Mufasa, by construction, they all match the stellar mass function quite well. If they didn't, they would tune their model more until they could match it. And so this indicates that you can match basically the same observational constraints with very different models for outflows. And it's possible that other observations can break degeneracies, like observations of the circumgalactic medium, for example. I think that's a very fruitful avenue for research, which a lot of people are working on. But this is still something, this question of what drives outflows and the resulting scaling relations, like the mass loading factor and also the outflow velocities with galaxy properties, that's still an active topic of research. So first I'm going to talk about in more detail these fire simulations with resolved stellar feedback, and specifically the properties of star formation, which is very bursty, and outflows in the simulations. So the fire simulations originally presented in Hopkins et al. 2014. Fire 2 is this 2017 paper. It's become a fairly large collaboration at this point, so there's a lot of papers that are coming out on the archive. The key aspects are that these are very high resolution cosmological zoom-in simulations where we can resolve the structure of giant molecular clouds. So this, of course, it's easier to go to better mass resolution and lower mass halos. So the spatial and mass resolution depends on what halo mass we're simulating, because zoom simulations are focused on individual halo, but also include the large-scale cosmological environment. But so in the lowest mass galaxies, so let's say a 10 to the 10 solar mass galaxy at redshift 0, the state of the art in the fire simulations are reaching masses of order 100 solar masses for particle mass resolution. So we really have a clumpy, turbulent ISM that is resolved at least the largest scale GMCs, sort of the driving scale of turbulence, a bit down the turbulent cascade. I mean, there's certainly smaller scale structure that isn't being resolved, and we worry a lot about whether that matters. But we're getting into the regime where we can actually start to resolve the structure of the ISM, unlike in simulations like Illustrious and Eagle, where their resolution is kiloparsec scale. And so really they just have these smooth disks, and all of the structure of the ISM is incorporated via subgrid models. So these simulations explicitly include multiple stellar feedback channels, approximate treatments of them. One of them is supernovae explosions, both type 1a and type 2. Of course, type 2 are prompt, and so after a few megayears, you have the first type 2 supernova going off. So sorry, I'll step back a second. So one important aspect is that the way that star formation is implemented here is that we have a prescription for computing the molecular gas density, although in practice that doesn't matter that much because it becomes of order 100%. At the densities that we're talking about. Then the gas has to be above a density threshold, which this depends on which simulations I'm talking about, the halo masses, because there's, of course, a maximum density we can resolve. But numbers to keep in mind here are 100 or even 1,000 particles per cubic centimeter. So we can actually resolve the densities of GMCs. Of course, not the highest densities that are relevant, but again, for comparison, in the large volume simulations, their star formation density threshold is like 0.1 particle per cubic centimeter. So you're talking about diffuse ISM densities. So we require that the gas is above that density threshold, and also that the gas is locally self-gravitating. And so if so, then we assume that the gas that satisfies those criteria is converted into stars at 100% efficiency, so per freefall time. What actually happens, though, because of this stellar feedback, which now I'll go back to describing in more detail, is that the efficiency, even though we assume an instantaneous efficiency of 100%, the actual efficiency you get out is not that high. It's maybe 10% or lower. And again, the details depend on what regime we're exactly talking about here. And the reason is that after those first stars form from that dense gas, very soon you have the type 2 supernovae going off. We also have an approximate treatment for radiation pressure on dust grains from massive stars, and then stellar winds and photoheating. And so what happens is that the dense gas is forming. You have a collapsing cloud. The first stars start to form. You have the stellar feedback processes very soon starting to occur. And on a time scale shorter than the local freefall time scale. And you're able to disrupt that dense GMC before it can convert 100% of its mass into stars. And so despite assuming instantaneous star formation efficiency of 100%, the actual local star formation efficiency is less than 100% because of the stellar feedback. And then as you already saw in the plot that I showed here, the global star formation efficiency in the sense of what fraction of the gas that I accrete under my halo do I convert into stars, that's also much less than 100%. And these two quantities are related, of course. So this slide, I show animations of one of these halos from the fire simulations. This is a halo that reaches a mass of 10 to the 12 solar masses at redshift 0. On the left, you see a three-color composite image of the stellar light, including the effects of attenuation from dust. On the right, you see the gas density color-coded by temperature, with magenta being the coldest, green intermediate, red is something like 10 to the 8 Kelvin. And what I want you to mainly take away from this picture is that the transition's already sort of happening, but what you probably noticed if you're looking especially at the right, at the gas, you see that at high redshift, in this simulation, the formation of this galaxy is a very violent, chaotic process where you have a lot of material falling in, you have bursts of star formation and outflows where a lot of the gas is being blown out. A lot of times the cold gas completely goes away. There's not a long-lived disk at early times. However, when you get down below around redshift 1-ish or so, you start to see that process becomes a lot calmer. The outflows become weaker. You don't have the gas being blown totally out, just some more galactic fountaining where the gas rains back down. And you have the presence of a well-ordered rotating gas disk. And if I rotated this, you would see that it ends up being quite thin. Because one of the other things in these simulations is that we cool down to 100 Kelvin, so we're able to get thin disk galaxies in the simulations. And so by the time you get to redshift 0, you have this very nice spiral galaxy that's just evolving very calmly. It's still forming stars. It's not quenched. One important detail is that these particular fire simulations don't include feedback from active galactic nuclei. That is something that we're working on in the collaboration. But in my talk, that's going to be completely neglected.
How once the baryons that are initially in the halo get cycled through dense atomic molecular gas phase?
So that's something that definitely depends on the mass and redshift. And I don't have representative numbers in mind at the top of my head, but we have a couple of papers that look into that in detail, so I'd be happy to show you those or provide you the references for those.
And also I'm asking questions about when feedback acts on molecular gas in these simulations, what's the dominant process by which molecular gas is destroyed or redistributed?
Yeah, so that depends a lot on the surface density that you're talking about. So for example, the radiation pressure on dust grains, at the very highest surface densities, this can actually become very important because in that case, the optical depth can become greater than unity, even out in the infrared. And so you have multiple scattering on dust grains that enhances the radiation pressure. For sort of more Milky Way-ish type surface densities, type 2 supernovae are the dominant channel. And then for lower mass galaxies, for dwarf galaxies, supernovae are still important, but photoheating can actually be important also. So again, that's something that is dependent on both. It's really mainly on gas surface density. I mean, metallicity also plays a role. But so as a result, you have dependencies on redshift and mass because of that.
How does the average gas density in the galaxy change just as a function of redshift? The ambient density.
The ambient density. Well, I mean, galaxy gas fractions are typically going down as you go to lower redshift. So that's sort of the secular trend. that if you just look at like a population average, the overall gas content is just decreasing, and I think that the highest densities would typically be around redshift 2 or so, where you have massive halos and you still have a lot of gas around, but then because of accretion from the IgM, cold flows shutting off, no longer being efficient, and then also combined with the consumption and these stellar feedback processes, you end up having lower gas fractions. But again, you have things like the mergers you saw that are frequent. I mean, those cause significant fluctuations in the gas density, and especially in the low mass galaxies. So Kareem Al-Badri, who is I think he's still a grad student at Berkeley, but he may be a postdoc, I'm not sure. So he looked into this and also the stellar velocity dispersion, and found in the dwarf galaxies, because of the stellar feedback, the violent nature of this and the burstiness, which I'll show you, you actually have extremely large fluctuations even in the stellar velocity dispersions, and also the typical gas densities of say, the molecular gas fraction, for example. And so these are very stochastic. And again, we may have a plot showing this number, but I can't quote something out of mind.
The density, the gas density, average gas density was larger than it is today.
Yeah, I believe that's correct.
So like by how much? Like an order of magnitude or less?
Yeah, I'd have to, if I had to wager, I would say that sounds roughly reasonable, but I'd have to think about that more. So this slide shows how the star formation in these simulations is very bursty. What this is showing is the specific star formation rate, so the star formation rate divided by the stellar mass, versus look-back time for a period of around redshift 2 for the same halo that I showed in that animation. So redshift 0 halo mass of 10 to the 12. The different lines are showing different strengths of feedback. So the black line here, this is just showing the fiducial feedback model. And one important thing that I neglected to mention is that things like the supernovae rate and the amount of momentum and energy coming from stellar winds, et cetera, those quantities are taken from stellar evolution models. And so these are not something that we're putting in free parameters and then tuning them to get good matches to observations. We're just trusting that that community, they're giving us the right answer, and then we're using that as input to the models. And then there's approximations because we're not resolving all relevant scales, but those fundamental inputs are not something that are free parameters. However, in this slide, we actually reduce the strength of that. So we just arbitrarily reduce the momentum and energy injected from these different stellar feedback channels by a factor of 3 and a factor of 9 for the weak and very weak cases, just to demonstrate the effects of the stellar feedback. And so what you see is that in the fiducial case, taking those numbers as given, you have these very large swings in the specific star formation rate, can be even an order of magnitude over sort of 100 megayear timescales. Then when you reduce the strength of the feedback, the amplitude of the variations in the specific star formation rate is reduced considerably. So this gives us a hint at what is causing this very bursty star formation in all galaxies of all masses at redshift 2 and in low mass galaxies at low redshift. That's the stellar feedback. And so this comes out. Part of this is that the star formation is very clustered in these simulations, both in space and in time. And this is because we actually are resolving the formation of clouds from gravitational instability, and then having stars only form in that dense gas. And so where stars form is localized, and thus where the stellar feedback occurs is localized. And then when you disrupt these clouds, especially with low mass galaxies at high redshift, often a few clouds are dominating the total star formation rate. And so when you disrupt those few clouds, it takes some time before you form new clouds and start forming another star cluster. And the other aspect about this is that this star formation drives a lot of outflows, and especially in the lower mass galaxies, it can actually evacuate a large fraction of the dense ISM. So that's why I was saying that if you looked at a given galaxy, the sort of mean density within the disk, it fluctuates quite wildly in time, at least at high redshift. And so as a result, you end up getting this highly time variable star formation.
You said it drives an outflow. This outflow, is it just unbound from the galaxy or from the halo?
So as most things, that depends on the mass and redshift. when your potential well is deeper, like naturally as you would expect, a larger fraction remains in the halo, so it's kicked out and you have this galactic fountaining. Whereas when you go down to lower halo masses, then you can much more efficiently kick out gas, and then it just escapes completely. So this is something, I mean, in the paper that was discussed in the group meeting, in Norm's group meeting today, that's addressed a bit there, because I was looking at the origin of the CGM, but this is addressed in more detail in a paper, Muratov et al. 2015, where they look at the fraction of the outflows that are being kicked out beyond the virial radius versus just staying in the halo. And this is something using the particle tracking pipeline that was used for that CGM paper discussed today. We have more detailed outflow analyses ongoing. But qualitatively speaking, at least, the fraction that escapes the halo increases as you go to low halo masses and can become of order 100% at the lowest halo masses. So what this plot shows here, this is for a selection of halos at redshift 2, going from low stellar mass of 10 to the 8 up to a stellar mass of around 10 to the 10. And this is showing a 200 megayear period, the star formation rate versus time. And for the spikes in star formation, these bursts, it's showing the amount of stellar mass that's formed in that star formation, in that particular starburst. So what you see, like in this lowest mass galaxy, it forms effectively 100% of its mass in that single star formation event. And then the star formation just drops off, and then it starts again later on. We just wanted to show the details of individual bursts here. Whereas if you look at the higher mass galaxies, you see that there tend to be more bursts within this 200 megayear period. And let's just look at this one, for example. So the total stellar mass is 10 to the 9.4, and the amount of stars you're forming in individual bursts is always less than 10 to the 8. So individual star formation events, individual star clusters, if you will, are forming a relatively small fraction of the overall stellar mass at that point. And you can see this point visually here, which is showing the exact same galaxies at redshift 2, but now it's the stellar surface density. So again, in that very low mass dwarf galaxy, you see that it's just basically a single star cluster with, I guess this is maybe some tidal features there. As you go to the highest masses, you see that there's an underlying stellar distribution that was built up previously, and you can still see the lumps of stars that formed recently, but these are not dominating the stellar mass at that time. So one of the things when we look at this kind of plot, and when we would show this to observers in particular, they would say, this can't be right. Galaxies can't have star formation that is this stochastic, because we observe this so-called main sequence, that relatively tight relation between star formation and stellar mass that I mentioned previously in the introduction. So this is something that we investigated in a paper led by Martin Spar, who's a postdoc at IAP at the moment in Potsdam. What he did is he applied stellar population synthesis to the simulations, taking the star particles based on their ages and metallicities and neglecting dust attenuation in this particular work. He computed the H alpha and far ultraviolet luminosities. So this is one case where the information that you get from observations and just directly from your physical quantities in the simulations, it might not always be fair to compare them, because the star formation rate tracers like the H alpha luminosity or the ultraviolet luminosity, they have some inherent timescales. So H alpha, you're relying on massive stars that are ionizing the gas around them. This is a recombination line. So of course, once your ionizing photon production decreases significantly after of order 10 megayears or so, the exact number depends on whether you include the effects of binarity in your stellar population synthesis models. But in any case, at that point, you no longer have any H alpha. So roughly speaking, H alpha is sensitive to the star formation rate averaged over, let's say, 5 megayear time scale. Ultraviolet is a longer time scale, something like of order 100 megayears, 50 to 100. This depends on the detailed star formation history, for example. And infrared could potentially be even longer. And so when you want to compare with observations of galaxy star formation rates, sometimes it can make a difference whether you go ahead and go through the extra step of computing synthetic observables versus just taking your instantaneous theorist-derived quantities that in order to know in reality, we'd have to sit around and actually count stars in the galaxy or ask God or something like that. So we take this step when it's important potentially, and we see whether the conclusions change. So anyways, what Martin did is he computed the star formation rates derived from both of these tracers. So here you see star formation rate versus stellar mass for redshift 0 and for redshift 2. The simulations are the points with error bars here, where this is showing the range is coming from that stochasticity in time of the star formation rates. And then in this case, because we have many more galaxies at redshift 2, because some of the more massive galaxies that we had at the time were only run down to redshift 1, we had a larger sample, so the curves with the points with error bars overlaid are showing the median and the standard deviation of that population. And then the observations are the green diamonds with error bars. And here the error bars, it's actually slightly deceiving. We should have made this plot a bit differently. This is showing the interpublication variance. This actually isn't the scatter in that main sequence. But you can remember I told you that was something like 0.3 DAX or so. And so roughly speaking, the amount of variability as judged by the scatter in this main sequence in the simulations seems to be roughly consistent with observations. One discrepancy we have is that at around redshift 2, the normalization of this relation is lower in the simulations than in the observations. And this is a generic problem in theoretical models that people are still debating. Some recent works have argued that this has to do with some observational systematics, perhaps. Just because it's such a robust disagreement between the observations and the models, people are sort of looking at other ways to get around this. But anyways, I'm more interested in the scatter in this talk. And this is only a crude measure of whether the amount of burstiness in the simulations and the observations agrees. You can actually do better than this, because as I explained, the H alpha and ultraviolet luminosity in particular, they're sensitive to star formation averaged over different time scales. So you can use that to your advantage by comparing those two indicators that can tell you at what point in these burst cycles you are located, if these burst cycles are occurring. So just to go back to one of these, so let's just look at a starburst, let's say, here. If I'm right here at the peak of the starburst or 1 or 2 megayears after that occurred, I have a huge amount of young massive stars around that are producing a ton of ionizing photons. And so I have a lot of H alpha emission, also a lot of UV emission. Fast forward, let's say 20 megayears. Again, ignoring the effects of binarity, let's say I have no binarity. I have basically no ionizing photons being produced from massive stars compared to the initial rate. So my H alpha decays very, very rapidly. But I still have a lot of ultraviolet emission coming from older stars than 10 megayears old. And so if I looked at H alpha, I would see that drop off before I saw the ultraviolet drop off. And so if I look at the H alpha to UV ratio, that can tell me whether I'm in sort of at the peak of the starburst or whether I had a recent starburst and I'm right after it. And so if we look at the distribution of this ratio, this tells us about the stochasticity of star formation. So that was the main point of this paper. What this shows here is that ratio of the star formation rate inferred from the H alpha computed from the simulations to the UV star formation rate from the simulations versus stellar mass. This is at redshift 0. The simulations are both the blue points, and then you have the line with the error bars showing the standard deviation. And then observational data from around redshift 0 from Dan Weiss and collaborators, you see as the red dots within the black shaded area. One of the things I want you to take away from this plot is that at redshift 0, at galaxy stellar masses of around 10 to the 10 and higher, this ratio is always of order unity, meaning that there's not short time scale, meaning tens of megayear time scale fluctuations in the star formation rate. However, as you go down to lower stellar masses, you see that there's actually quite wide dispersion in this H alpha to UV ratio, which one interpretation of this is that there actually are significant fluctuations in galaxy star formation rates on tens of megayear timescales in lower mass galaxies at redshift 0. And this is true both in the observations and in the simulations. And we know in the simulations this is why this is occurring, but there's also other issues potentially here having to do with things like dust attenuation. But this is something that the observational community has really been adopting in recent years, that this ratio is a good probe of the amount of stochasticity in star formation on these timescales. One discrepancy between at least the Fire 1 simulations and the local group, or the local galaxy observations, is this population at around stellar mass of 10 to the 9 or so, that we have a lot of simulations with very low H alpha to UV ratios, that you don't see any observed galaxies in this region of the parameter space. And so this may indicate that the feedback process is too violent here, that you're sort of over-quenching the galaxies. This could also be a resolution effect, however, because as I explained, especially in this older generation of the fire simulations, you're only resolving the most massive giant molecular clouds. And in principle, if we resolved all the way down the mass function, it may be that, OK, we disrupt the giant molecular clouds, but we still have a few smaller ones forming and providing a sort of floor on the H alpha emission that we're not capturing in the lower resolution simulations. So it's something we haven't actually remade this plot with the more recent higher resolution simulations, but that's something that we should do to see how sensitive that is to resolution now that we have simulations with over an order of magnitude better resolution at fixed halo mass. So it seems that modulo that caveat, the overall trend in the burstiness of the simulated galaxies is consistent with observations, and that this very bursty star formation is not inconsistent with the observed star formation main sequence. And one of the questions, of course, is that many times when people see this, and even the name main sequence, it sort of has a bit of a connotation that galaxies are evolving along this sequence, and then their star formation is quenched. They pass through this green valley transition phase quickly and go into the quench phase. So often it's interpreted as an evolutionary sequence. And so we asked, is this actually the case in the simulations? And it's not the case. So what this is showing is the star formation rate versus stellar mass. These are for 4 different halo simulations, just showing the star formation rate, how it fluctuates around. You end up getting the main sequence if you just look at in a population sense, taking the simulations at different times, considering those to be independent galaxies, which is obviously not 100% correct. There could be some effect from the halo growth histories that cause galaxy to galaxy systematic variations. But the fact that you have this very short, very significant short timescale variability in star formation rates means you do capture a large amount of this scatter. So anyways, what you see is that these galaxies definitely do not evolve along this main sequence. They jump around a lot in the star formation rate stellar mass plane because of these variations. But as you've already seen previously, you still get a main sequence out when you look at this as a population.
You spend an equal amount of time in each segment?
No, so you definitely, I don't have the plots in here, but the burst phases, I feel like I'm stuck repeating the same thing. That also depends on mass, but in the lower mass galaxies, the amount of stellar mass that you form in these bursts is almost 100%. So like in that case of showing this this galaxy up here, like in this galaxy, you form 100% of the mass, and something that that ends up to be a dwarf at redshift 0, the integrated stellar mass, much of it was formed during these short bursts, whereas the amount of time spent in the burst is maybe less than 20% or so. Whereas in the more massive galaxies, there's a transition in terms of at around above redshift 1, you're spending, again, of order 20% of the time in the burst phases, and you're forming a smaller fraction, but still a lot of the stellar mass in those phases, whereas at redshift 0, you're forming basically none of the time in these burst phases. But generally, when you do have this very bursty star formation, they're not the dominant fraction of the time, but they definitely can dominate the amount of stellar mass formed. So this just goes back into that point of the amount of variability of these individual simulations. What this is showing is cumulative distribution functions of the specific star formation rate of individual simulated galaxies at redshift 2, around redshift 2, below a stellar mass of 10 to the 10 and above a stellar mass of 10 to the 10. And what you see here is that, so the hatched area, this is showing this so-called main sequence, in terms of specific star formation rate. And so galaxies to the left would be considered quenched galaxies if you didn't have any information about their time evolution, just looked at them in a snapshot in time, measured that star formation rate at that stellar mass. On the right would be starburst galaxies. And so what you see is that individual galaxies over a 200 meg-year interval, this is all that's being shown here, they can go from being classified as starbursts to quiescent galaxies because of these very significant short timescale fluctuations in the specific star formation rate. However, as you go to redshift 0, you see a qualitatively different picture in the high mass galaxies. Again, low mass galaxies have very large fluctuations in the star formation rate. High mass galaxies, however, at least the 6 halos that we had at the time, they all, during their entire 200 megayear period around redshift 0, they have specific star formation rates that are consistent with the main sequence. So they're not quenched, they're not starburst, they're not fluctuating wildly. It's like you saw in the animation that I showed. It's just this very steady, kind of ordered disk galaxies that are forming stars at roughly a constant rate. Oh, sorry, I actually do have this plot in here. Let's look first at the right. So at redshift 2, the blue line is showing the fraction of the total stellar mass that's assembled in these burst phases. And then the black is showing the fraction of time versus stellar mass. What you see is that in the lowest mass galaxies, you're forming of order 100% of the stellar mass in the burst phases. The high mass galaxies, you're forming as much as something like 40%. However, you're always spending only about 20% of the time in the burst phases. Most of these are these temporary periods of quiescence with very low specific star formation rates. When you look at redshift 0 instead, again, in the low mass galaxies, you're forming most of the stars in the burst phases and spending maybe 30%, 20, 30% of the time in the burst phases. Above a stellar mass of 10 and 9.5 or so, you're forming none of the stars and spending none of your time in the burst phases. So the picture you should have in mind here, and sorry, what time should I wrap up actually? Around 3? OK. So what's happening here is you have this cycle of bursts and outflows. This is shown in this plot from Sasha Muratov's paper, which is showing for, again, the same halo. So the halo mass at redshift 0.5 is around, this is the halo that becomes halo mass of 10 to the 12 at redshift 0. So it's 8 times 10 to the 11 at redshift 0.5. It's showing the star formation rate as black versus time. Then he computed the outflow and inflow rates in just thin spherical shells around the galaxy. So the thick dashed lines are at 1/4 of the virial radius, and the dotted lines are at the virial radius. The red are showing the mass outflow rates, and the blue are showing the mass inflow rates. And so what I want you to take away from this is that generically you see this sort of pattern, that you have a peak in the inflow rate. Well, the peaks in inflow, outflow, and star formation all tend to be co-located in time. And if we look at this in details, like say do a cross-correlation analysis, what you see is that the peaks in star formation tend to occur around the time of the peaks in inflow, and that then the peaks in the outflow are shortly after the peaks in the star formation, because the stellar feedback processes are delayed by 5 to 10 megayears after the star formation events, so the outflows are being driven after that. So at high redshift, in all galaxies, you have this cycle of accretion, gas surface density getting high, forming large clouds through gravitational collapse, having a burst of star formation, soon a strong outflow, and then you have no longer have really any dense gas in the ISM, and you have a low specific star formation rate. Then some fraction of that material, again depending on galaxy mass, rains back down in the galaxy, resupplies the disk, and you have further gravitational collapse and formation of stars, and you restart this cycle here. When you go to below redshift 1 in these high mass galaxies, you no longer have this cycle. Instead, you have a relatively constant star formation rate. The outflow rate is also constant. And one thing to note is that in the previous plot, you see that the outflow rate is much higher than the star formation rate. So this mass loading factor that I mentioned is much greater than unity. When you look at the massive galaxies at low redshift, in this case, the mass loading factor is less than unity. The outflow rate is less than the star formation rate. So this is part of the reason why you can just have this constant star formation. You're not kicking out a large fraction of your ISM. And then the mass inflow rate is very low. You don't have efficient accretion in these massive halos at late time.
Why is the mass loading factor higher when the inflow rate is higher?
Well, so the reason, so that was actually the second part of the talk, which I will only advertise, and I'd be happy to discuss more. So one of the big questions is, why do the outflows become inefficient in these high mass galaxies? And so this is something, I'll just skip over this here, that cross-correlation analysis I mentioned. So this is something that we set out to address, to try to understand. Phil Hopkins and I developed a toy model that provides a possible explanation for this. And I'll just like I said, I'll just basically advertise this, and I'm certainly happy to talk to anyone about this in more detail, but I won't be able to do it full justice in the amount of time I have here. So in this model, this is an extension of models like from say, Norm and Todd Thompson, Elliot Quatert and collaborators, also Ostreicher and Shetty, where they're models for self-regulated star formation, considering that stellar feedback is depositing momentum. So what I mean by this is that you have a disk that is marginally stable. Tomb rate Q is of order unity. The disk is supported against gravitational collapse by turbulent pressure. So star formation and thus the consequent stellar feedback are injecting momentum into the surrounding ISM. They're driving turbulence, and so that's providing pressure support against gravity. And if you have the star formation rate increase, then it ends up puffing up the disk, and the star formation rate ends up going down, and then you have less momentum injection, so it's sort of a self-regulating equilibrium system. What we did in this work is that we used, motivated by a paper from Mark Krumholtz and Todd Thompson, which the point of their paper, they pointed out that, so in particular in the models that I mentioned from Norm and Elliot and Todd Thompson, for example, they just consider a mean gas surface density, right? But in a real disk galaxy, you have, even for a given mean gas surface density, you have a turbulent medium. And so you have a distribution of surface densities if you look at subpatches of that disk. So what the paper by Todd Thompson and Mark Krumholtz pointed out is that if I have a disk that is globally below the Eddington limit, I can still have some subpatches of the disk that are locally super Eddington. And so we applied their formalism to these self-regulated star formation models in order to compute the gas outflow rates in this sort of simple analytic toy model framework. And so the idea is that I have this stellar feedback that's driving turbulence. I have some distribution of gas surface densities at a given time. The low surface density patches, those for a given, for a constant rate or constant over larger scale rate of momentum injection, you're going to more easily accelerate and eject the parcels that are at low surface densities. And so my criterion to say that gas is being blown out of the disk is that the gas has to be the patch has to be sufficiently low surface density that you can accelerate it to the local escape velocity before the turbulence fills back in. You can imagine a chimney, and turbulence is trying to fill in this chimney. So you need to eject that parcel quickly enough before you fill that chimney in and block further momentum deposition to that parcel of gas. So I'll skip through this. So in this kind of model, you end up predicting a Kanika-Schmidt relation, the relation between star formation rate surface density and gas surface density that's broadly consistent with observations, which is one of the successes of these. A big caveat, as there's issues with getting the total gas surface density from tracers like CO, but I don't want to get into this, especially given the time. But this is part of the reason people like these simple models. Skip that there. Right, so now the bit about outflows. As I said, you can make this criterion that locally I have to accelerate the patch to the local escape velocity to blow it out. When I go through this argument, I can get, what this means is you end up getting a critical gas surface density below which the gas goes into an outflow. The patches of the disk, the subpatches of the disk that are at higher surface densities, what you're doing with those is that you're only driving turbulence and preventing further gravitational collapse, but they're staying within the disk on the turnover timescale of the turbulence. At the very high surface densities, that's the stuff that's going to actually collapse and form stars, but that's typically at any given time a relatively small fraction. So what you can do is you can predict scaling relations for the mass loading factor in this simple analytic model. And I'll just show you now this cartoon picture that I was describing. So this is the idea. I have a analytic disk with some given mean surface density here, the gas surface density. But if I look at subparcels of this disk, say patches that are of order the disk scale height in radius, they're going to have a distribution of surface density. So I have this log normal PDF. This is shown as the local gas surface density as a ratio to the mean gas surface density. So below unity, underdense patches, above unity, overdense patches relative to the mean. The picture in mind here is that above this critical surface density, this is where you're just driving turbulence and keeping the gas in the disk. Going to lower surface densities, that's the material you can accelerate it quickly enough that you blow it out of the disk before you fill it in that chimney and block further momentum deposition. So what happens is when you have sufficiently high turbulence, the width of this PDF, that depends on the Mach number of the turbulence. And again, I apologize, I couldn't go through the derivations here, but we have relations for how that depends on the galaxy properties. So when you have high turbulence, you have this critical density threshold is located at relatively high surface density, still slightly below the mean in this particular cartoon, but it's in the core of the log normal. And also your log normal PDF is broad. And so a significant fraction of the total disk mass can be driven out in an outflow. However, when your turbulence becomes weaker, specifically this ratio of the turbulent velocity dispersion to the galaxy circular velocity, which in this self-regulated model scales as the Toomre Q times the gas fraction of the disk. What happens then is you get this picture where you have a less turbulent medium, so you have less variations in the gas surface density on small scales, a sort of more smoother disk. And also this critical surface density moves to a lower underdensity. And so what happens is that when this threshold moves out of the core of the log normal, you end up getting that a negligible amount of material can be blown out of the galaxy.
Something I don't understand. So the feedback here that you're considering is stellar winds and supernova. These have zero color. So where is the turbulence coming from?
Sorry, these have?
Zero color. It's just divergent to both.
So this is sweeping a huge amount of stuff under the rug, obviously, as a toy model. All that we're taking here is we're considering the amount of momentum that's injected per unit stellar mass. So if you look at people that do simulations of supernovae explosions in inhomogeneous ISM, and they look at the amount of momentum that ends up being coupled on larger scales, we're taking that number as input. I mean, also that's an input to the simulations. So in the toy model, we're using this as input, and I would say that in detail, when you look at those simulations, you don't have a completely homogeneous medium. So I think from inhomogeneities, then that probably arises. But that's something that we're not at all addressing here. It's just saying the rate of momentum injection is giving you, it's pumping up the turbulence on the length scale of order the disk, and then setting force balance with gravity. So that's really small scale physics that we're relying on smaller scale simulations for that.
Can you just clarify one thing? So star formation, the Bursty star formation is happening at the high column density end of this distribution, and the ejection is happening at the low column density end. So obviously, in order to eject stuff, you have to get the high column density material in contact with the low column density regions of the disk. How's that exactly happening in this picture?
Yeah, so in this picture, what's happening here is that this is really considering the pressure support of the diffuse ISM. So this is not even explicitly considering this disruption of the GMCs. I mean, we really kind of sweep the very highest surface densities under the rug here, but instead it's saying that, excuse me, more the overall disk, not the self-gravitating collapsing clouds, but sort of the diffuse ISM, that's the part that's marginally stable, and you have to maintain that marginal stability so you don't have sort of catastrophic fragmentation of the entire disk. And so the idea is that you have some dense cloud that is being disrupted, and that's being folded in the local star formation efficiency, and then that momentum is being injected to less dense material on larger scales than that, just in the diffuse disk.
You're assuming you can sample the distribution twice in a sense. So you're assuming that it's uncorrelated with the fact that you had the burst of star formation and this low column density
Yeah, so one thing this is assuming is that the momentum deposition is smooth on larger scales than the fluctuations in the gas surface density from turbulence. And that is a point where we haven't checked that in detail with high resolution simulations, that might be a bad assumption. And that's something the referee pointed out, and we state that that's certainly a caveat there and may not hold in detail for sure. So I'm already over time here. So just the takeaway point of all of this, we fold this toy model in with some empirical scaling relations. What you see when you look at the resulting mass loading factor versus stellar mass at different redshifts. So black is redshift 0.25, blue is redshift 1.25, green is redshift 3. The mass loading factor coming from the simulations are the points here, and then the lines are for this toy model. What you see is that you get this suppression at the high mass end. When you go to redshift 0, your outflows cut off. They're rapidly suppressed. And that's because, given these empirical scaling relations, massive galaxies have sufficiently low gas fractions at low redshift, whereas the lower mass galaxies have gas fractions above this critical threshold. Because, as I very quickly said, in this toy model, that's a key parameter that sets the ratio of the turbulent velocity dispersion to the galaxy circular velocity, which then controls where this threshold is. So at all redshifts, very crudely speaking, the low mass galaxies are in this sort of regime, whereas at high masses and high redshift, this is where galaxies lie. But those high mass galaxies, once their gas fraction drops down below this critical threshold, they move into this regime where they no longer have sufficiently turbulent ISMs, and thus they don't have these strong outflows. And so that's what you see here. So I'll show that again. So just in summary, with these fire simulations, which are very high resolution cosmological zoom simulations with stars forming out of dense locally self-gravitating gas and explicit stellar feedback, you see very bursty star formation in low mass galaxies at all redshift. High mass galaxies only about above redshift 1 or so. And we think, as I very briefly said, that this could potentially be explained by considering this how turbulence determines the distribution of gas surface densities and what material you can blow out efficiently with this toy model. And we think that this transition is key for the emergence of, we see in the local universe massive galaxies. We often see nice, thin, cold gas disks. And that's something that we only see in the simulations once this bursty star formation and resulting strong, gusty outflows subside. So we think this is important in order to have the massive galaxies like how they look today. And then conversely, low mass galaxies, they don't look quite as pretty in that sense as the high mass galaxies, even at low redshift, probably because they're still very bursty and still have strong outflows even at redshift 0. Thank you.
Do you have anything that would be triggering burst starvation below redshift 1? Because if you don't have something that would like merging or interactions or sort of strong bars in the galaxy.
Right. So, I mean, the issue of triggering it can also be that there's just enough gas there, and this issue of maintaining marginal stability and driving this turbulent medium. So you have some GMC forming. You have the stellar feedback that's locally disrupting that, depositing some momentum into the diffuse ISM, keeping that disk stable for a bit. But then some overdense patch, because of turbulence, decouples, becomes locally self-gravitating, starts to form stars again. And you also have this fountaining process. So when you do have that outflow, even though in the very lowest mass galaxies, often most of it is escaping the halo. But for the low mass galaxies, there's still a non-trivial fraction that's raining back in as a galactic fountain on a sort of order 100 megayear or so timescale. And so you're resupplying the disk. And so then you can cause it to be unstable again because of that gas resupply. So that's sort of a trigger in some sense. And I mean, so we haven't done a systematic study on how much mergers are triggering these bursts of star formation, but certainly some of the strongest bursts do seem to be associated with mergers, and that's occurring still even at low redshift, but they're not frequent enough that that's the dominant process here. Yeah, but you still have that cycle that's really just, it's not triggered, it's just driven by this process of the expelling gas, some of it raining back down, and gravitational instability,
Right.
marginal stability.
Okay. I mean, I guess low redshift, you shouldn't have 0 galaxies released bursts or outflows, right?
No, you certainly don't. In the simulations, at least, even at low redshift, the lower mass galaxies are still very bursty and have strong outflows. And I mean, you see the former, you see like in Dan Weiss's observations, that's one interpretation. And there's a lot of other work that's indicated low mass galaxies have bursty star formation even at redshift 0. And then you certainly see outflows in low mass galaxies at low redshift.
But not high mass.
Well, you see at the highest, so one of the things I didn't mention is that those scaling relations are for sort of typical galaxies. So that doesn't apply if you had a galaxy like, say, an emerger with a particularly high gas surface density, or a galaxy that has a much higher gas content than average. So observationally, you do see for high gas surface density massive galaxies in the local universe, you see strong outflows. But this model, that's not inconsistent with this model. It's just saying that as the general population of massive galaxies at low redshift shouldn't exhibit strong outflows with high mass loading factors, right? That's the other important thing, is the mass loading factor is what matters.
Any other questions?
What processes are you get resolved that you look like?
Well, I mean, there's a lot. So I mean, still, especially in the massive galaxies, we're still relying on as I answered in response to one of the questions a bit, the way that we're coupling the momentum coming from supernovae to the surrounding ISM, that's still relying on a subgrid prescription in the results of these simulations that are setting up somewhat idealized inhomogeneous ISM, putting in clustered, unclustered supernovae. So in principle, it would be much better if, even in a very massive halo, we are resolving every single individual supernova remnant. I would say that's one important thing. Also, the fact that these are not doing full radiation hydro, that could be important. The fact that, related to that, so the radiation pressure relies on, that's radiation pressure on dust grains, and these simulations are, well, we're not even doing the radiation hydro, but even people doing radiation hydro are typically assuming that the dust and gas are perfectly coupled, but they're starting to actually treat the dust as a separate fluid, and so you could imagine that at some point, sufficiently low density, they become decoupled, and that's no longer an efficient mechanism for driving outflows. So that's not a question, that's more a question of physics included than resolution, but yeah, there's certainly a lot to be done there. Resolving further down the turbulent cascade and GMC mass function could be important for some things.
So if you launch